Uh, okay, so yes, my name is Carmelo. I'm an engineer at ONF. I'm one of the native Italian speakers that Robert mentioned before in the room, but Robert, you did great, so your pronunciation is good. So yeah, in this session, we're going to talk about P4 runtime. If you don't know ONF, among other things, we build SDN controllers, so we're really interested in runtime control and ways to support new devices like P4 devices in ONOS. So I'm gonna give an overview of the API. I'm gonna talk about the workflow. How do you go from a P4 program to a control plane? We're gonna have an exercise that involves tunneling, and this will be taught by Brian O'Connor. And we'll conclude with a demo of an actual controller platform like ONOS. So if it was not clear, the focus of the session is runtime control. So once you've wrote your P4 program and you compile that to a target-specific configuration binary, you load that into your data plane, and then you have the same tables you define in your P4 program. And maybe you would like to find a way to insert, modify, remove entries on those tables, or maybe control other entities of your P4 program. This is what P4 runtime does. It enables you to control those entities. So before presenting P4 runtime, let's have a look at some of the existing approaches to do runtime control. One possible approach is to use the auto-generated P4 compiler, the runtime APIs that are auto-generated by the P4 compiler. I don't know if you know about this, but when you use P4C, you can also get auto-generated, I think it's C++ API, that basically if you define, for example, 5 tables, then you will have a number of methods for each table to add, modify, delete entries. This is cool, but the problem of this approach is that this is program dependent. So if you decide to load a new program onto your data plane, then we are to do that without restarting the control plane. Another alternative is the BMV2 CLI you saw in the previous exercise. This is program independent, but it's target specific. So the control plane you wrote that used the BMV2 CLIs is not portable to other targets. Then we have OpenFlow, and OpenFlow was initially designed, created to be target independent. But the problem of OpenFlow is that this is protocol dependent, so the adders and actions are actually baked in the specification. If you take the example of the previous exercise with this, what we call the MyTunneling protocol, if you would like to control a device with that MyTunnel P4 program using OpenFlow, then you will need to extend OpenFlow. The same thing for the Open Compute project size, which abstraction interface. It's target independent, but protocol dependent. So it seems we identified 2 important properties or requirements of our runtime control API to control our P4 switches that are target independence and protocol independence. None of the approaches we mentioned before satisfy both properties. And guess what? A group of people sit down and decide to create a new API, new protocol called P4 runtime. So what is this P4 runtime? P4 runtime is a framework for runtime control of P4 targets. If you go check out that repository, you will find both the API definition and the server implementations that run on the switch and that vendors can reuse to add support for P4 runtime to their targets. It was a contribution by Google and Barefoot, and now this is in the end of the p4.org API working group. This is working in progress, so please expect changes to the API. The API is protobuf based, meaning that you can easily generate code to serialize and deserialize those messages for many different programming languages. And also, it uses gRPC for the RPC framework. So again, it's easy to generate code, for example, for the client part that runs on the control plane for many programming languages. As I said before, this API is program independent, so the API itself doesn't change when we change the P4 program. And not just that, but the P4 runtime itself allows you to push to load a given P4 program to your target. And that's why we say that P4 runtime enables field reconfigurability. So what does this API looks like? Let's assume you would like to insert an entry in a table defined in P4. Then what the control plane needs to do is to send a table entry message. This table entry message needs to specify the ID of the table and a sequence of field matches, an action, and maybe other properties like a priority or controller metadata. In the case of field match, each field match needs to specify the ID of the field, and then the type of match, for example, exact, ternary, longest prefix match. And if it's exact, then it needs to specify a byte string for the value. If it's ternary, a byte string for both the value and the mask. If it's longest prefix match, then you need to specify also the prefix length. I see one question.
Are you just describing the serialization format, or is this something that you actually have to sort of write yourself, or is this at a different layer of abstraction that I'm like confusing?
Yeah, good question. So this is an expert from the P4 runtime protobuf definition. So the control plane needs to write messages that adhere to this specification. I have an example later on. So yeah, this is the actual API defined using protobuf. And this is what you find in the repository I showed to you before. I talk about the field matches. For the actions, it's the same thing. You need to specify the action ID and a sequence of parameters, each one with its own ID and a byte string representing the value. So to summarize, for the control plane, right, to be able to insert a table entry, control plane needs to know a number of attributes, like the IDs of the entities, like tables, field matches, actions, parameters. The field matches that are supported by a particular table, their match type, bit width, and the parameters for the particular actions, and so forth, so on. So if the writer of the control plane is also the writer of the P4 program, then maybe he already knows all these attributes, but maybe there's also a more convenient way to get all this information. And this convenient way, it's called P4info. P4info is a file generated by the P4C compiler. It captures a number of P4 program attributes that are needed at runtime. So it captures, for example, the IDs for tables, actions, parameters, the table structure, match type, etc. It is, again, based on protobuf, so it's easy to serialize and deserialize this P4info file into your control plane. And it's very important, this is target independent. So if you use the P4 compiler to generate the P4info, given the same P4 program, you will get the same P4info for different targets, for example, BMV2 or an ASIC target. So the P4info affects the control plane and the P4 runtime server you see in this architecture, while the other output of the P4C compiler, for example, in the case of the BMV2 JSON only affects the data path. So you can see the P4info is a contract between the control plane and the data plane on the content of the API of the messages. So let's see an example. Let's assume we want to use the same basic router P4 program we saw in the example before, in which we have a PV4 forward table, a PV4 forward action, and a PV4 LPM table. This is what you see on the right. It's the output of the P4 compiler, the so-called P4info. You can see there is, we have an action section in which there is specified the IPv4 forward action with its ID and the parameters required by these actions, like destination address with where the value needs to be 48 bits, port with 9 bits value. The same for the tables. There's a table sections. In this case, we have the IPv4 LPM table with this integer IDs that we need in the P4 runtime message, and the sequence of match fields with their type, bit width, name. And also we have a reference to the action ID supported by this table. So once we have the P4info, the control plane can now, in the case of table entries, insert one of these table entry. So assuming the same P4 program of before, and assuming this table entry we want to add, so in this case, we're adding an entry to the IPv4 LPM table that matches on this IP address and that executes these actions with these two parameters. The control plane with the P4info on one end will need to generate this protobuf message. So this is very similar to the protobuf definition I showed you before. The only difference is that here we have the different fields populated. So we have the corresponding table ID, a sequence of match fields, each one with its ID, like the one we saw on the P4info. The value in this case uses protobuf byte encoding. the prefix len, because the table defines longest prefix match. In this case, we're matching on the whole 32 bits of the IP address. Same for the actions. In this case, we're specifying the ID of the action IPv4 forward with 2 parameters. The first one, which is the MAC address, and the second one, which is the output port, again in byte string encoding for protobuf. So the cool thing is that if you want to control a network of P4 devices from different vendors, if the control plane and the data plane, at least the P4 runtime control server on each device, they all share the P4 info, then you will use exactly the same target-independent protobuf messages to insert table entries on those devices. And the same thing happens if you want to maybe control your data plane from a switch local control plane. So if control plane and data plane shares the same P4 info, then you will use the same target-independent protobuf format. So the bottom line here is that not only P4 runtime is target-independent, but the same API can be used equally well both by a remote controller or a local controller. Now, let's consider another example. As I said before, yes, there's a question?
For the table IDs in the distributed model, is there consistency between table IDs, or the controller needs to be aware of table IDs?
Yeah, that's the purpose of the P4 info. So if you want to install a table entry in your IPv4 LPM table, the controller needs to know the integer IDs of that table, and that's where it is given to you in the P4 info. So there is a one-to-one mapping between table names, integer IDs. And then the integer IDs are those used in the actual P4 runtime API.
Are those identifiers stable as you add or remove, fields, or change width of things, or sort of tweak your table entries, or change your, I guess what are those entries? Are they just generated new in sequence every time? So if you extend your protocol, then the IDs will change, or are they stable?
I think we have one of the P4 runtime creators in the room that can answer this question.
Yeah, so they are stable. For instance, if only if you change the table name or the control name inside which the table resides, then the ID will change.
Okay. So as I said before, you can use P4 runtime also to push a new P4 program onto the switch once the switch has been deployed. So for this, the P4 runtime.proto definition defines an RPC call called setPipelineConfig that is used to push down the pipeline config bits. What is this pipeline config? Pipeline config is basically the combination of the P4 info file and the target-specific configuration binary. So for the case of BMV2, the pipeline config will contain the P4 info and the BMV2 JSON. If you're using another target that uses a different format for the target-specific configuration, then you will need to add that bits into the pipeline config message. So this is how we push a new P4 program onto the device. And once we push that program, we can use the other calls to install table entries. Yes?
Okay, so 2 questions. One, is BMV2 an expectation for P4 runtime, or P4 runtime can run regardless of BMV2?
I'm not sure I get the question.
I mean, does P4 runtime expect a BMV2 control plane interface, the BMV2 CLI or that interface?
Yeah, so P4 runtime implements the device-side API, but then you need a target driver that connects those P4 runtime calls to your target below. In this case, BMV2. So in this case, BMV2, yes, offers a target driver for P4 runtime.
Because BMV2 initializes itself based on the P4 program. But
Okay, good question. Good question. So there is a way you can start BMV2 with no P4 program.
Yeah, my question was, should set forwarding pipeline config be the first way to bootstrap things?
Yes.
Or it can, the ASIC come up with itself and then subsequently you can keep changing the.
No, the set pipeline config is the first call the control plane needs to do towards the device to initialize it. Because again, the fundamental part here is the P4 info. That is the contract for all the subsequent API calls that will happen. So first thing, both control plane and data plane needs to share the P4 info. Okay. And in this case, BMV2 will also provision the data path with the new JSON configuration.
So just follow-up question on that. When a P4 program changes, so I mean one of the aim of P4 runtime is here. So one of the aim of P4 runtime is to push new P4 program. So ultimately, the P4 info is what changing when we push the new P4 runtime program. Basically, no, I mean, which is device independent config, right? Mm-hmm. So expectation is that when we are pushing new P4 run program, ultimately P4 info is what should come as, right? Because right now when I run BMV2, what happens right now, BMV2, and when we give the P4 program's JSON file to controller, it just passes that as a P4 device config, basically just that file as device config. I think it's plainly wrong, but ultimately the P4 program, which is device independent, should come as a P4 info. So is this currently going to, I mean, will this be fixed in P4 BMV2 right now or no? Because right now what I see is the P4 JSON version of the P4 program is actually comes as a P4 device config. Is that wrong, or is that what is the expectation? Because that JSON file contains the whole P4 program, which is also device independent. Did you get my question?
Well, I'm not sure the BMV2 JSON is device independent. I know if you go look in the BMV2 repository somewhere, it's written that BMV2 JSON should be target independent, but ultimately there are some artifacts in the P4C BMV2 compiler that produces a not really target independent description of the pipeline. You can see the P4 info as a subset. All the information you have in a P4 program and then in a BMV2 JSON. For example, in the P4 info, there's no specification of the primitives that are called in a specific P4 action. It only tells you what's the action name and the parameters and the bit width of the parameter. So it's really a subset of all the attributes, properties of a P4 program that are needed at runtime control. I don't know if I answered your question.
Somewhat you have answered. So my specific question here is basically the P4 info ultimately should contain everything which is device independent, right? I mean, right?
Yes.
So if is the P4 info is a subset of device independent configuration, or is it the complete? Ultimately, let's say some device want to, let's say, doesn't have any device specific configuration for the sake of argument, right? Mm-hmm. So and the whole P4 program is basically device independent, mm-hmm. right? Can each and every construct in the P4 program be translated into the P4 info, or is just a subset of that? So ultimately what I want to do is, let's say if my device is basically doesn't need any device specific configuration, I just need to pass this P4 program to the controller. Okay. And all the information should come to me as a set forwarding pipeline config so that I can initialize my whole pipeline, right?
Yeah, then in this case, you cannot use the P4 info. P4 info is only a description of the APIs. There's no information about, the implementation of the actions or the apply logic of the control flow. So you still need a target-specific configuration file.
No,
I don't think there are plans to have the P4 info describe the actual logic and implementation of your P4 program.
So there's one missing piece.
Maybe we can let,
P4 info contains only the attributes that are needed by the controller to program flows, for example. Right? So it would have no notion of table A is applied before table B or not. Right? It would only have the attributes that table has an ID, all the match fields have IDs, and when the controller is creating a flow to program in the switch, it would use those attributes to compose the flow and then push down the P4 runtime using the P4 runtime API.
That's exactly what my understanding was, right? So right now, let's say if somebody wants to, when we, with the P4 runtime, we cannot directly pass the P4 program to the switch. It has to come through the control plane via set forwarding pipeline config, right? And that P4 program cannot come, it's not basically, you only told that, we can't, P4 info is not for that, right?
Yeah.
Now the program is device independent, so which parameter it will come through?
If you have a target, that is, you would have a target specific compiler, P4 compiler. BMV2 can be thought of just as another target.
Okay,
It's
so
a soft switch target.
So requirement is that controller should compile the P4 program into target specific blob, and we pass that as a device config.
P4 device config. Yeah.
That sounds like a defeats
The
the purpose of
controller
P4 runtime.
doesn't have to do it on the fly, right? So you have a P4 program. Offline, you can compile your P4 program for a given target, and then the controller can pick up this blob, right, for your P4 program.
Okay. Just follow-up question on that. So does it mean that we require controller to have all the, at least compilers of all the devices which it's controlling? So it will actually make sure that, this guy is talking to this one?
Absolutely, yeah.
But actually, I think it is, in a way, it defeats the purpose, right? But ultimately, P4 controller should not know, in a way. Ultimately, the P4 program should be passed as it is, and then this guy, the device, the P4 runtime server layer should do compile and then, install it. That's what looks like the right architecture to me.
I think this is an interesting discussion we can take offline about the design of all the runtime control infrastructure.
So, at least you accept that there are some of the holes which are there is still under the, because I'm also attending the P4 runtime work group, so I have these questions. I thought maybe this is the right form where I can ask these questions. But if it's not, then I think I can ask.
Yeah, no. I'm suggesting we take this offline because of time constraints. Because we also need to do an exercise about P4 runtime. And maybe that will clear, also give you an answers of the questions, because you will see P4 info instance. This is part of the exercise. So let's do a quick recap of what we just saw, the P4 runtime API. We covered a few things, like the P4 info. What is this P4 info? How do we insert table entries? How do we format the table entry message? And also how we load a new P4 program and pipeline config to the device. There are a number of things we didn't cover, such as how to control other P4 entities that we will discover during the rest of the day, such as externs, counters, meters. How we implement OpenFlow-like packet in, packet out support, such that we can send packets from the data plane to the control plane for further inspection. We enable controller replication using, for example, master-slave arbitration. This is supported in P4 runtime today. And how we enable, for example, batch reads and writes. There is something else, which is switch configuration. So let's assume you wanna, as soon as you connect the switch, your controller, you want to bring up the ports, you want to know what the ports available are, you want to know the speed and other attributes of the ports. This is what we call switch configuration. Well, this is outside the scope of P4 runtime. The P4 runtime API targets, again, runtime control of P4 entities, so anything you can write in P4 and can be controlled at runtime. P4 runtime will enable to do that. Switch configuration is outside the scope of the API. And this can be achieved using other mechanisms that are under the investigation of the p4.org API working group, such as using OpenConfig models and via GNMI. And this is pretty much the end of my presentation about P4 runtime. And yes, very important, this is a work in progress, so please expect changes in the future. And I would like to leave the stage to Brian O'Connor that will present the exercise.
Thanks, Carmelo. So actually, I'll show you a couple slides to introduce things, and then we'll jump into the exercise. So what we're going to do today is we're going to take a look at the P4 basic tunnel program that we created just before Carmelo's presentation, before the break. And we're going to take the control plane piece out of the BMV2 CLI and move it into a Python script that's going to act as our remote controller. So the controller in this case has a number of responsibilities. First, it has to establish a gRPC connection. gRPC is the default transport for P4 runtime. And so we're going to create a gRPC connection from your Python script, which is called mycontroller.py, to each of the BMV2 switches. In this case, we're just going to use switch 1 and switch 2. It's the same topology you saw earlier, and we're just going to ignore switch 3. But you could use switch 3 if you want to kind of go on for extra credit. The second thing we're going to do is we're going to use the set pipeline config call that Carmelo was talking about to push the output of the BMV2 P4 compiler to the switch. So the switches are going to come up in this case without a program. The question before asked, do you have to push it via the controller? No, the P4 program could be there and you could retrieve it via a get config. You could also push the program via your NMS or other network management or control system and just read it from your controller. But the controller does need to be sort of program aware in the logic that you implement. So your job is going to be to establish the same tunnel that we did earlier using the BMV2 CLI. So in this case, we've added a little bit, 2 extra actions to the program. We've added a tunnel ingress action. So this is going to match on a destination IP, and it's going to map the traffic into a particular tunnel ID. Then there's the mytunnel forward action, which we saw before. This is the one you're going to write. And then the mytunnel egress rule, that's a new action that we've added to the program that's going to pop the label off, the header, the mytunnel header off the packet and egress it out to the host. And then finally, we've also added a new concept, which we've implemented for you, which is we've added counters to the program to count the number of packets that are coming into the tunnels and the number of packets that are leaving the tunnels. And we do this just as a way to help you debug the rules so you can see the traffic in the controller. It also shows how a controller could be monitoring various entities that P4 exposes and then using those to make control decisions. So getting started, there's on the VM already loaded in the P4 2017 fall directory an exercise called P4 Runtime. The place to get started here is with the README. So if you go to if you prefer to view it via the GitHub viewer, the Markdown might be a better place to look. The area of emphasis is going to be in the function called write tunnel rules in mycontroller.py. And for the demo, I'd recommend you have two terminal windows. One, we're going to run the data plane, which is the 3 BMV2 switch topology we saw earlier. And the other is going to be where we run the controller. So just to give you a slight orientation, a small orientation, clear this. So I'm going to run the data plane just using make, so you can do the same thing. In P4 Runtime, if you look at the directory, let me just remove the pcap files. Make it a little easier to see. You'll see that there's the advanced tunnel P4 program. This has the 2 new actions that I just told you about, as well as some counters. There's mycontroller.py, which is going to instantiate the gRPC connections, push the pipeline config, et cetera. And then you'll notice that there's this directory called P4 Runtime libs, or lib. In here, we've created a couple of helper libraries. BMV2.py is how we do the device-specific encoding of the pipeline to send over the gRPC connection. Switch.py is a wrapper around the switch connection. So we're going to make the calls to gRPC on your behalf. For people that haven't programmed with gRPC before, you can look there to see how the calls are being made, but the messages are actually going to be constructed in there and then sent to the switches. And then we've got helper.py, which is it understands the P4 info and is going to provide a dictionary-like translation. You can go from IDs to names and names to IDs to figure out how to convert the table name to the ID number that's required for the message. And then there's also convert, which is just a simple helper function so that IPs and MAC addresses get encoded into byte strings and vice versa. So we're going to give you about 10 or 15 minutes to start on your own. I would start in mycontroller.py. You'll notice that the method of interest is write tunnel rules. And yeah, we'll be passing around, or the TAs and Carmelo and I will be walking around helping to answer any questions that you have. So just a quick show of hands. How many people have made some progress? Good? And leave your hand up if you're done, if you've finished the exercise. Okay, just a few. So there's 2 things we can do. I can either show you the solution, or you guys can take this home and work on it. So if you want to see the solution, show of hands. A few. If you are wanting to not see the solution, no one. Well, 1. Okay, so maybe you just close your eyes. Okay. So as I said before, the area of interest is the write tunnel rules method. Just so you guys know how this is invoked, at the bottom of the Python script, there is a function called main. So this is all that stuff I was telling you we do for you. We instantiate the P4 info helper, that's the dictionary. We establish a connection from the my controller Pi to your switches. We set the forwarding config on the devices, and then we write 2 tunnels. One tunnel is from host 1 to host 2. So switch 1's the ingress, switch 2's the egress. We give it a tunnel ID, and then the destination, and then the others in the opposite direction. So the code that you needed to implement is the code at the top in write tunnel rules. So first we write the tunnel ingress rule. I'm just going to copy that down below as a starting point. And then we'll implement the transit rule. So using the first rule as a starting point, the first thing that we need to do is we need to target the correct table. So we're going to do the my tunnel exact table. That's our first order of business. The second thing is that on the my tunnel exact table, the header field to match is the my tunnel dest ID field. And then because it's an exact match, we can just provide the tunnel ID, which I believe is just called tunnel ID, but we'll double check, tunnel underscore ID. So for the my tunnel exact table, we're going to match on destination tunnel ID. And then the action that we're going to perform is we're going to perform a my tunnel forward. And the destination ID is going to be, my tunnel forward takes a port, I believe. Double check. So it's below. So it takes a port, and then one of the interesting things about this example, to make things simple, we've just hard-coded the port at the top of the file to always be 2. If you remember the topology, if you remember the topology that we showed you, ports 1 were connected to the host, and ports 2 were connected to each other switch. In general, you're going to want to have some better model of the topology where you can actually query the topology and figure out what output port you're going to want to send to. In the ONOS side, in the ONOS demo, you'll see just after this, you'll see how we do that. And then we're going to write this entry to the ingress switch. So if the demo gods are with us today, then we can run this and it'll work. So I've already started the topology. I'm going to start a ping from H1 to H2. And then we're simply going to run the program. So we can run mycontroller.py. And you can see that we installed the ingress rule. This was a copy-paste problem, but it should say forward tunnel rule, and then the egress rule. You can also see that we're going to read the counters, and we expect there's a ping going every 1 second. So we see every 2 seconds, the counters on all of our tunnels are incrementing. And the ping, just normal ping that comes with the Linux distribution is sending traffic between over our tunnels. So that's the demo. Hopefully you were able to absorb that. And what we're going to show you now next is a little bit about ONOS. So I'll try to keep this brief because I realize we're standing between you and lunch. So what is ONOS? ONOS is an open network operating system. It's an open source project that started at ON Lab. It's hosted by the Linux Foundation. And it's a controller platform that Carmelo and I work on primarily as our day job. So ONOS is a distributed system. It's an active-active controller, if you will. There is a distributed core at its heart where you have high availability, scale out, and high performance. We also provide a number of core abstractions These are to sort of make it simple to write applications that are not device or even southbound specific. And then we also have a great deal of modularity. So you can extend various core subsystems. You can add applications to the platform and new southbounds without having to rewrite everything. So as I said, a lot of core subsystems. These cover a lot of parts of just general networking state. The ones in red are the core ones. The ones in gray are primarily due to just keeping the distributed system up and running. We have some apps, northbound interfaces on the top and southbounds. For the purposes of the demo, I just want to focus on a few of them. We have a few primitive services, device, link, and host service. These are an inventory of the network elements you have. We have a flow rule service. This is the equivalent of the write rule that we were just using in the demo. We have a packet service. This is for getting packets off the data plane and sending them over P4 runtime. We aggregate these inventory elements into topology. Network config is a way that we tell ONOS what the network is expected to look like so it can make the connections. And then we have a path service, which we're going to use to compute the paths between the ingress and egress points, so we don't have to hard code a port number. Carmelo's written a MyTunnel application, which is basically a Java implementation of the Python demo we just did, and then we're going to run this over P4 runtime. So what you're seeing on the screen, in the top left corner, we have a mininet topology. In this case, we're going to use a slightly more complicated topology than we just saw in the demo. We're going to use a torus topology, where your neighbors, east, west, north, south neighbors are connected with links. So this is a heavily looped topology that a normal network would struggle with. In this case, we'll do a 9x3 torus, so 27 total switches, and it's 54 bidirectional links. ONOS models them as unidirectional, so you'll see 108 links in ONOS. In the bottom window, Carmelo's started ONOS, and you're seeing the ONOS log. And then in the top window, Carmelo's going to have the ONOS command line interface. So we can take a quick look at what apps are running on ONOS once the SSH connection's been established. There we go. So you'll see that there's a lot of apps that get started. In ONOS, if it's a driver, if it's a southbound, if it's a northbound piece of functionality, it gets loaded as an application. This enables you to add and remove these apps at runtime without having to restart the whole controller. The app of interest in this case is the last one in the list, which is P4 tutorial MyTunnel. So that's been loaded. We'll start the topology now. And as you can see, we're going to start the 27 switches. ONOS is connecting to them at the bottom, and it's also, when it's connecting to them, it's been configured to use the advanced tunnel program. So once this all comes up, we can take a look at the ONOS UI.
We got 26 switches, not 27. It's okay, it's fine.
One of the BMV2s didn't come up?
Yeah.
Okay.
Anyway, it should work anyways.
So this is another one of the northbounds to ONOS. It's the UI. And you can see we have a torus. Kind of looks like a donut, if you remember from advanced math or geometry. So in this case, you can see each of the switches is a BMV2 device. Each of these switches is going to have some default flows. ONOS uses LLDP and BDDP for link discovery, and then it also snoops the ARP traffic to do host discovery. That's how we've done it.
Should we do the ping?
So yeah, so we can, Carmelo's example has been programmed so that when ONOS detects a host, it creates a tunnel between any known hosts in the network. So he's going to ping from one side of the torus to the other side of the torus. You can see the pings are working. In the bottom view, you can see the rules that ONOS has decided to install. It has a tunnel ingress rule on the ingress device, several tunnel forward rules, and then a tunnel egress rule on the egress device. And then if we look at ONOS, we can turn on the packet counters and see the path that was selected.
But there is some glitch in the
UI?
Yeah.
Oh.
It's because of the failure. Anyways.
So that gray switch, it typically means it's offline. So that might be the one that's missing.
Yeah.
If we look at the flow rules that show up in the UI, you can see that there's now been 2 forwarding rules that have been added. This is one of the intermediate switches. So I guess the takeaway here is that you can use the Python script and the libraries that we've provided to implement a remote controller. But what we've found is that there's a lot of nicety to having an inventory of devices, topology, path computation service. The other nice thing, which we're not showing here, is that if you had a heterogeneous network, some OpenFlow devices, some P4 runtime devices, your application can be written in a program and protocol agnostic way. So the flow rules that Carmelo is writing could just as easily be flow rules that are targeted for an OpenFlow device, assuming that the headers are present in OpenFlow. So with that, I think we'll close. We'll let you go to lunch. And Carmelo and I are both around for questions if you have any.
Few takeaways. Okay, so.
Oh, sorry.
It's okay. P4 runtime takeaways. So to conclude, what we can say is that today we learned that P4 runtime is a program-independent API, meaning that the API doesn't change with the P4 program. You use always the same runtime API, and there's no need to restart the control plane when you want to load a different P4 program. The second takeaway, it's very important. Maybe we didn't put enough focus on this, but the device, so if you want to use P4 runtime, the device does not need to be fully programmable. Indeed, can be used also with fixed function devices, provided that the forwarding behavior of your target ASIC can be expressed using P4. And you can see how if you're able to express that using P4, then you're able to generate a P4 info, and then you're able to tell the control plane how the API should look like. Finally, it's protobuf based, the format of P4 runtime, meaning that this is a well-supported serialization format in many languages, and also and is supported by many RPC frameworks like gRPC. So it's easy to auto-generate client-server code for different languages. If you want to write a controller in Go, just auto-generate the client side of the service. And for this reason, because we're using gRPC, there's no need to define common RPC features like authentication or session management, and et cetera. And with this, I conclude my talk.